So they could say like one stupid thing, and then people like would just be like, "Oh, I don't know how to understand it," and then it's just like the whole thing.
All right, let's get started. So as some of you may have noticed, I'm not the professor. The professor is out of town today, so I'll be talking about, I'll be doing a lecture. We're taking kind of a slight digression, and we're going to talk about searching and sorting, and we'll try applying it a little bit to the Facebook example. But searching and sorting are kind of like fundamental problems in programming. You'll probably learn about them like in 6 other classes if you stay in programming. And there's also, I know a lot of you are having interviews, so this is also good interview material. These are pretty popular questions. Okay, yeah, I'm not used to the room, so if I'm writing too small or if you can't hear me in the back, then just raise your hand and tell me. All right, so we're gonna start off with searching. So at a high level, like completely unrelated to programming, searching is basically just you have a bunch of objects and you have one specific thing you're looking for, and so you just find where it is in like a pile or whatever. So some of you may have been exposed to searching if you finished the CRM lab. Basically, you had a customer database, and you need to check if a customer existed in the database or not before you insert it to make sure you didn't have any duplicates. And that's a good transition into linear search, which we've mentioned a little bit in the past. So I'll start off with an example. So let's say you have the array. So just these 8 elements. We're going to do integer arrays to begin with, and you'll see why it makes a little bit more sense. But let's say we're doing linear search on this, and we're searching for the number 15. So the approach we probably took for the customer database is you have an iterator, let's say x, and you'd be iterating through this array left to right, and you check to see if this element is equal to what you're looking for, if this element is equal, and then so on. So if we're looking for 15, your x will start off at the beginning of your array, and then that's not 15, so you'll move on to the next one. That's not 15, move on to the next one, and then so on and so forth until you reach your value of 15. And so as soon as you see that what your current iterator is on is equal to this, then you can say, okay, I found my element. Let me return index 5. And then whatever was looking for this element could then access array element number 5, and it would be 15. So let's say we decided to look for the number 8. 8 doesn't exist in here. So we'll do a similar process. Start off with our iterator here, and move on, and move on. We keep moving on until we reach the end of the array. And our iterator is now an element that doesn't exist in the array. So if we ever reach this situation, then we know that the element was not in the array. So this should be familiar, so I'm not going to spend too much time on it, but I will write the code on the other side. Basically, let's say you have your function int linear search. And you have a, which is your array, then you have a size, and then you have the element you're looking for. The way this function will work is basically you pass in the array, you pass in the size. This is the element you're looking for, and in that example, maybe it's 15. And then what it'll return is the index of that element if it's found in the array, or -1 if it's not found in the array. So once again, kind of speeding through this, and slow me down if you guys get confused. But you'd have a for loop, which starts at 0, and goes up to the size of your array. And then if you see a of this index is equal to the element we're searching for, then we can just say, all right, we found the element, let's return the index. Now, if this loop completes fully, and it never passes, passes this condition, it will never return. And so, essentially what that means is we've reached the end of the array because x is greater than size, and we didn't find the element, and so we can just blindly return -1 down here. All right? Does this make sense? Yeah, I'm hoping this is familiar. Yeah.
When you return -1, is -1 universally false?
Good question. And no, that's not necessarily the case. So, in the case of like this search, where we're just returning an index, what is an array element? What is an array index of -1? Right? It doesn't make sense. In fact, you can return any negative number, and you can't index that into the array because it doesn't exist. So, if you're doing a search like this, where it returns an index, then yeah, you can use -1. And I'll return to this near the end, when I'm going to basically apply this to the user database from Facebook. So, good question. Okay, now let's dig into this a little bit. Let's say we were given that array over there, and we're searching for the element 8. So what is the worst case number of iterations you have to go through before you realize 8 doesn't exist? Yeah, it'll be size. So the worst case is basically this one down here, where you iterate through every single element, and once you're at size +1, then you realize, oh, it's not even in this array, so I have to return -1. And if we kind of abstracted it a little bit, the general, it's called complexity, is n for a linear search, where n is the size of your array. And this isn't necessarily every single case. If you look at this 15 that you're searching for, you didn't have to go through all n elements, but in the worst case, you do have to check all n. And we're going to talk about this briefly during this lecture, but the professor will pick up more on Wednesday. And this is actually this is something that's also pretty like fundamental, and also makes for really good interview questions. So these two lectures are very applicable to what you see in the real world. All right, so n elements. Unfortunately, if we have like a random set of elements in the array, then you can't really do better than n worst case, because n worst case, if you don't know any ordering or it's just some random data, then you have to look through all of them to see if the data exists. But what if we could put a constraint on the array so that so we don't have to take n elements? We can do something to this array so that we may not have to search all n elements. So can anyone think of what that might be? Yeah. So I heard sorting. So sorted arrays. Let's go ahead and just sort this one. Let's sort this array. You get 1, 3, 4, 6, 7, 9, 11, and 15. And let's go ahead and just, let's write the indices of these elements above. Okay, so the sorted array has this really nice property, where if you pick a random element from the array, let's say 7, then you know everything to the left of 7 in this array is going to be less than or equal to the value 7, and everything to the right of this element in the array is going to be greater than or equal to 7. So some of you may have, this may be making some sort of sense how we could use this to our advantage and create a more optimal search. So let's say we're looking for the number 3. If you just randomly pick an element, let's say 7, and we see like 3 is less than 7, then we can say, okay, we don't care about any of that stuff, we just care about this part of the array. And so let's pick a random element from here, let's say we pick 4. then once again we know 3 is less than 4. So all of this is useless to us, and it's going to be in one of these two elements if it exists in the array. So now we have these two, we can pick another random element, and let's say we just happen to land on 3. So now, in just 3 iterations, we found the value 3. And it may look like this is less efficient because you could have just found this in one iteration of linear search. But let's say you had an element up here that you're looking for. So let's repeat that again. Let's say you start with 7, and this time you know that 11 is greater than 7, so you only care about this part of the array. And you pick one of these elements at random, say 9, then you know that once again you need to go to the right side of this array, and then you have these two elements and you pick one. And so in the average case, you end up taking a lot less iterations. So let's build up this example a little bit more, and try to write some code for it. So I mentioned you pick a random element, and you partition the array basically into a left side and a right side. So let's start off with the full array. We'll put an L here and an R here, indicating that this is the left index and the right index of this array. And instead of picking a random element, let's just pick something right in the middle. So if you take the average of these two numbers, 0 plus 7, and divide that by 2, you get 3.5. And integer arithmetic would say, okay, let's just turn that into 3. So let's take that as the middle element. So this would be a single iteration of our search. Now let's go ahead and look for the number 3 again. What we know is the middle element is too high. So what we need to do is shrink this effective array, and we can do that by changing this right index. So what do you guys think would be the best place to put the right index? At M? Okay, so at M. So there's actually something a little bit better that you can do. M minus 1. Now the reason you can do M minus 1 is because you know that this element right here is not what we're looking for. Otherwise, we wouldn't even be performing this next iteration. And so we can just disregard that entire part inclusive of this M. And we just move 1 over to the left. And then in this case, since we only care about the left side, we don't move L. And so L stays in the same place. Now if we perform the calculation for the center again, you get 0 plus 2 is 2 divided by 2. And we end up with the element, or with M pointing to what we're searching for. And at this point, since we're searching for the number 3, we're already done. Our midpoint is now looking at 3, and we can just stop right there. So this is to get 3. Let's try getting 4. We'll start off with a very similar position where you're looking through the whole array, and your midpoint is right there. Once again, 4 is less than 6, and so we can shrink this array into this range and put our midpoint right there. Now we're actually less than the number we're searching for. So we do a similar process except for the left side. What we did previously was we took, up here, we took our midpoint and then moved left 1 to get to the new right side. And that's because we didn't need to check this specific element. So once again, we don't need to check this 3. So we can move the L 1 element to the right. And we notice that our L and R actually converge. And so if our L and R are the same, then our M will also be here when we do the midpoint. And we were looking for the number 4. And so now our midpoint is looking at 4. And so we're done with this search. So let's do one more example. Running out of space, so copy this. Okay. We'll start off with this, and this time we'll look for the number 8. So 8 doesn't exist, but we'll have to figure out a systematic way of figuring out that it doesn't exist. So the first iteration will look like this. The next iteration, now we're looking for 8, and 8 is past this midpoint because 6 is less than 8. So we'll set our new range to be left here, right here. And if we compute the average, we get 4 plus 7 is 11, divided by 2 is 5.5. And we'll just round that down and say 5 is our midpoint. This is still not our element, and now we've gotten past where we should be. So we'll move the right side over, and we'll converge L and R again. And then our midpoint will be in the same location. So now we see that the midpoint is not equal to 7, and the left and right are the same. But just for the sake of example, let's see what happens if we continue one iteration further. So we see that 7 is less than 8, and when a number is less than what we're looking for, then we move the left side, and we move it to m plus 1. And so what you end up in the next iteration is actually something like this, where the right side and the left side have now swapped positions. So now the right is on the left is on the right, and the midpoint is here. But the whole problem is that we've now swapped our sides. And this actually turns out to be kind of a nice condition. If our sides ever swap like this, then we're guaranteed that the element we're looking for is not in the array. So you could figure it out here, but you'll see when we start writing the code that this condition is actually kind of nice, and it reduces the code complexity a little bit. Okay, now let's actually write the code for this. So can I erase this? Did everyone got this done? Okay. I should also mention I'm recording the audio for this lecture, but I'm doing this on the board just so we can build it up. But I will be posting linear search, the next thing we do, and like all the code for today in the SVN. So you'll see all the code there. So don't frantically try to write everything down. Okay. So we're actually going to have a similar interface. Are there any questions so far on the algorithm? Okay. And we're going to name this bin search. So bin search stands for binary search. The reason it's called binary search is because every time you perform one iteration, you're essentially cutting the array in half. And so binary as in binary has to do with the number 2, and every time you cut it in half, it's divided by 2. So binary search. This will also make a little more sense in a second. Okay. Right off the bat, you'll notice the interface is exactly the same. So if you recall from the last lecture, we talked about the search function inside user database. And we had the search, which basically returned a user pointer, and it took in a database and an email address that you were searching for. So the interface for that was fixed, but the professor mentioned you can change the inner guts however much you want. And so that you can see that happening right here, where the interface is the exact same, but now all of a sudden we have a much better algorithm. Okay, so let's start writing the code for this. The first thing you want to do is define your left and right. So initially, your left side starts at 0, and your right side starts at size minus 1. The reason it's size minus 1 is because if you have 8 elements like this, then size will be index 8, but you want size to actually be index 7. So the 7 indicates the rightmost side of the initial array. Okay, so we've gotten these two set up, and now what we'll do is keep iterating until some certain condition is satisfied. So looking at this example, especially this one right here, can you figure out what this example would be, or what this condition would be?
While left is greater than right.
Okay, so while left is less than or equal to right. Okay, and once again, this condition is nice because of this property where if we continue iterating past what we have in our array, then the size will cross. And as soon as the sides cross, this condition will be false, and we'll exit the loop. Okay. Now in here, we mentioned we pick an element from this range, and we decided just for simplicity we'll pick the midpoint. So let's say int mid is equal to left plus sorry, these should also be L and R. L plus R over 2. This will give us the midpoint, and if you do if you have two integers and you're dividing by another integer, the compiler will automatically assume integer division. And so if you see the number 5.5, for instance, then it'll just truncate that into 5. So we have our midpoint. The first condition we want to check is if the midpoint is equal to our element. So our array is A of mid. If that's equal to LM, then we can just return this index because we found the element. Okay, what if we haven't found the element yet? Then we need to perform another iteration of the binary search, and we've changed the range so that we're looking at a different part of the array. So one condition for that is, let's say our midpoint is less than what we're searching for. If the midpoint is less than what we're searching for, then that means we're in something like this situation, where we want to move the left index to one past the midpoint. And so let's just do that. L is equal to mid plus 1. And then if this condition is false, then we want to move the other side. And we can do right is equal to mid minus 1. Okay, and that's the entire while loop. Does this make sense? How we're moving the pointers around and kind of cutting the array in half each time? Okay. So the last thing we want to do is, if this condition is false, and we've never met this condition to return an element, then that means we've reached the end of the array, and we haven't found our element. And so we want to return -1. Alright, so this whole algorithm is basically just an implementation of that. Now let's talk a little bit about how this thing performs compared to linear search. So in linear search, we said in a worst case scenario, you'll have n iterations, where you have to go through every single element one time, like in this array, to see if the element exists in there. With binary search, since we have this sorted array, and we have the property where we can identify which side of the array we need to go to, then we perform less iterations. But how many is less? In this case, we have an 8-element array. In this example right here, when we were searching for 3, it just took 2 iterations. So first we found midpoint and then cut the array in half. Then the next time we cut it in half, we found our number. So that's pretty nice. We got it in 2 iterations as opposed to potentially 8. But this example was a little bit worse. So for this one, we had to do 1 more iteration until these 2 values converged, and you were underneath the 4. Your midpoint was at the 4. So that was 3 iterations. And then even worse than that was this one, where in this case we had to iterate not until they converge, but actually 1 step past that, where they actually swap places. So in this case we had 4 iterations total. And our array was size 8. So every time we split the array, we split it in half, and so we have half the work to do. So if you look at it, the first time you had a full array to check, then you had half that array, then you had half that array, then you had half that array. So what that kind of implies is that we have something logarithmic going on. Every time we increment, or every time we perform 1 iteration, we have half as much to work with. And so as it turns out, the worst case of binary search is log base 2 of n, and then plus 1 for that potential case in which you have to in which you don't find the element, where you have to go the extra step and make the indices swap places. So log 2n plus 1. And now if you start plugging in some values, like even 8 for instance, if you have linear search that's potentially taking 8 iterations, in this case you're taking log 2 of 8, which is 3, plus 1, which is up to 4 iterations. So we're at half. If you have an even larger number, let's say like 128, then log 2 of 128 is 7, and we have plus 1, so we end up with 8 iterations for binary search as a maximum, and a maximum of 128 iterations from linear search. And so you can see this is significantly better. So, any questions on this? Yeah.
If you had like 5.95, it would still remain a 5.
Yes. Yeah. Just quickly on integer divisions. I thought you guys would study them through TK, but I'll review it quickly. Basically, integer division, if you divide by any number, then you're left over with some decimal if you do the conversion. But everything past the decimal point just gets killed. So it always rounds down. And that's how integer division is defined in a compiler, I guess. And you'll actually see kind of how this works and why it's better in classes like 460N. So yeah, for now, just assume that when you do integer division, then always truncates, even if it's like 5.99999. Okay, any other questions? No? All right. So some of you might be questioning the feasibility of having a sorted array, because binary search only works if your array is already sorted. And in some cases, you might have a sorted array. One example might be if you have a bunch of elements, and you're basically putting it into a new array, but every time you put it in the array, you make sure that you're putting the element in the correct location. So if you have, let's say 157, 153, and you're copying that into a new array, then you put this 1 in, and then you put this 5 in, and then when you put this 3 in, you're like, okay, it should be in between here, so let me just move the 5 out of the way and insert the 3 there. And so if you have data like this, and you can maintain this sorted nature of the array, then that's really nice to use binary search. But in most cases, you probably won't have data like this, and you'll have to perform a sort yourself. So I'm a little bit curious. Anyone can answer it. If you have, let's say you have a situation where you're just looking at a bookshelf, and you want to sort the books by author. So what are some of the algorithms, not really algorithms, what would you do intuitively with those books? What's a procedure you might do? Pardon me? Okay, last name of author. But let's say you see all these books and you want to actually sort this bookshelf. How do you, what steps might you take?
Break them into smaller groups.
Pardon?
Break them into smaller groups.
Okay, break them into smaller groups. So maybe you cut it in half, and now you're trying to sort each half independently. So what do you do to actually perform the sort, though? Alphabetically. Okay. So what I'm getting at is maybe
Take the books out of the bookshelf.
you could do that and just put them back in, similar to this. But what I was getting at is maybe you'll look at the authors and you'll say, okay, I have an author whose name starts with D, and he's the first guy, and then right after that I have an A. So you may take that author whose name starts with A, and just remove him from the bookshelf, move the D over, and then put the A author at the beginning of the array. And now you know that A is probably the beginning, so you look through the rest of the bookshelf, and you keep performing this procedure, just taking the lowest author you find and just sticking them into the front. That's one algorithm which tends to be the most intuitive of the sorting algorithms, and it's called selection sort. So we'll talk about that. And then we also have one called bubble sort, which I think you guys have seen. Have you guys seen bubble sort before?
Yes.
Okay. So yeah, I'll talk a little bit about that, and if we have time, I'll go a little bit more in depth in some other nicer sorts. Okay. So is everyone done looking at this? Let's do an example, and I guess I'll start with selection sort just because it's more intuitive. So. Okay. And I guess I'll use the same array I had, so I don't know why I erased it. Let's see here. 1, what was it? 11, 9, 4, 7, 6. I think that's correct. So let's say you have this array, and you want to perform a selection sort to get these elements sorted in ascending order. So what I mentioned selection sort is, basically, you look at this whole array, and you just find the maximum of it, this whole array, and then you just move it to the end. So the first iteration, let's say you have that iterator, you go through this whole array. So you find x, you assume this is the maximum. Look at 11, say, okay, 11 is bigger than that. So this is my current maximum. Then you move to 9, 3, 4, 15, and you see, okay, 15 is now the biggest element I've seen. 7, 6, and then when you're done with that iteration, you know what the largest element in this array is. That's 15. So now once you've done this, you can say, okay, I know this is the biggest, so let me just swap it with the end. And you can do this because the end, since you're sorting ascending order and you found the largest element, then you just move it to the end and swap whatever was there. And so that gives you one element. But you can notice that this array is not sorted yet. But what is kind of nice, since we moved the largest element we saw, we can now say, all right, we know this is the largest element, and so now we just have to sort this smaller array. So let's perform the same process. We'll assume we'll assume 1 is the biggest, and we'll see, okay, 11 is bigger, and keep going until we reach the end of this subarray. And then the subarray, or the maximum of the subarray is 11. So now you swap this with the second largest element. And so this becomes a 7. That becomes an 11. All right, let's go to the next iteration. But this time, we only need to consider this part. And so if you go find the maximum of this part, you find that it's 9. Perform this swap. And now you're in a even smaller subarray. And you keep doing these iterations until this bar basically is down here. So let's just go ahead and do that. Now the current maximum is 7. Let's swap that. Okay, move this bar over. The current maximum is 6, so you can swap that with the max. And then move this bar over. Now the current maximum is going to be 4. Perform a swap. And you may have noticed the array is already sorted, but the algorithm doesn't take that into account. It'll just still keep going. Move this bar over. Now the maximum element is going to be 3, and you can just swap it with itself, which puts it in the exact same place. Move this bar over, and now the last element in the array is 1. And if you have a single element array, it's kind of nice because you know that array is sorted. And so we don't even have to move and do this last iteration. We could just say, all right, now the whole thing is sorted. So this has kind of an intuitive nature. Once again, going back to that books example, if you see a bunch of books and you're trying to alphabetize it, you might look over the whole bookshelf and say, okay, this guy starts with Z, let me move him to the end. And then you look at a smaller section of the bookshelf. Maybe you have someone whose last name starts with Y, move that. And you keep performing these iterations until you've reached the first book, and you've already sorted the rest of the n-1 books, and then you're done. The whole thing is sorted at that point. All right, so does this make sense? Would you guys say that that's intuitive? Like, I'm actually just curious. Okay, so generally, yeah. As it turns out, there's been some study where people who know sorting algorithms, who don't know sorting algorithms are asked to sort something, and they just naturally, people just naturally gravitate towards selection sort. So I guess it's just inherently built into you, you just didn't know it. Now you do. All right, so let's write the code for this. Can I erase this? Yeah. Once again, I'm going to have all of this in SVN. I'll have all the sorts and searches that I write today. Alright, so now we're going to be sorting an array, and so the interface will be slightly different. Let's call this selection sort. And now we just have the array and the size. We don't need an element now because we're not searching, we're just sorting the entire thing. And we're also just going to sort A basically wherever it is in memory. And so this will be it's called a destructive sort, which it just, what it sounds like. You have this A pointer pointing to some elements in memory, and when this function is done, those exact elements will be in a different order. So, selection sort. Alright, so the code for selection sort is a little bit weird looking. You may have noticed there's definitely two sorts of loops. One of them is bringing this guy down. The other one is finding the minimum, or the maximum of the subarray. So let's write the outer one first, which moves that bar basically lower. So this for loop is backward, as in it's going from right to left. And so the bar starts off at size -1, inclusive of size -1, and then it ends up at 0 when we're finally done. And you could replace this with 1, that'd be fine as well. But let's just keep it at 0 for clarity. So now that we have this bar coming, what we need to do is find the current max.
I think it should be X.
Yeah, that's right. Thank you. Oh, like I said in the example, we'll assume that the maximum is just at index 0 to begin with. Once we have that decision, we'll have this for loop, which is the inner loop, and that goes from y up until x. So I mentioned earlier that this x is inclusive, and what that means is basically your bar is kind of like up here, but you do want to include this element initially because you want to search the entire array. So that's why this is a less than or equal to. Okay, now this part should be familiar. If the element that you're looking at right now, so a of y, if that's greater than a of max index, if that's greater than a of max index, that means the element you're looking at is greater than what you thought was the maximum. And so you can just set whatever max index is to your current index. And if you close this for loop, then, like I said, this should look familiar. This is just the normal, like, finding the maximum. The trick here is that you're finding a maximum from from 0 to x, because you're not finding the maximum with the entire array every time. Okay, so once you know exactly where the max index is, I mentioned you have to perform a swap. So for now, let's write this out as just a swap function, and we'll dig into that a little bit more in a second. So you want to swap the from array A. You want to swap max index with this current position up here. That's another one. Sorry. This current index here. And so x, like I said, initially is pointing to this, or has this index. You found the maximum. I think 15 was like here last time. So your max index is here. Your x is here, and so you just swap the two elements. And then the next iteration, our x will move from here to here, and then our max will be somewhere else, and we'll swap with x again. Okay? Is that clear? Do you see how these two correspond to one another? Okay. And that's actually the entire function. So now let's dig into the swap a little bit. It's pretty straightforward code, but it's a little bit unintuitive as well. So let's just write that here. Void swap. It takes in the array you're trying to swap from, and then it takes in two indices that you want to swap. So what you need to do first is make a copy of one of these elements. Let's choose a of x first. And then a of x is equal to a of y. So you've performed half the swap now. You've moved that y index into the a index. But you have to make this copy. And the copy is just there because you've only performed half of it. You've moved one value into the other, but you have to move that original value back into the other location. So you need to keep track of a temporary variable, and you just assign the other index equal to that temp. This should be, I think this should make sense. It's a little bit weird just because you have that temporary storage, but once you get past that, it's just pretty intuitive. So now, going through this whole thing again, just to reiterate. So you have this for loop, which is moving that bar from the right side to the left, one element at a time. And then in here, you're just finding the maximum of your current range, and then you just swap that into the last element. And so at the end of one of these inner iterations, you'll have your maximum element in the highest position, and then you'll move this bar lower, move it to a lesser index, do the same thing again, except now when you swap to the second or the highest index, and you keep doing this until you've swapped all the way down to the second index, and you just keep shrinking the array you're working with. Okay, so does this make sense? All right, so now let's talk a little bit about the performance of this thing. So once again, if we have n elements in our array, how many elements is the first iteration going to go through? We'll go through n. What about the second iteration? Yeah, n minus 1. What about the third iteration? N minus 2. And so on and so forth. So you may remember from math class, this ends up equaling n times n plus 1 over 2. And this is something that will come back later. For now, we can just leave it at this. But in the next lecture, we'll talk about why this formula is important. And we'll use it to compare this sort to other types of sorts, which may be faster. But for now, let's just say you have this many iterations, n times n plus 1 over 2. Okay, so that's selection sort. That's, like you guys said, it's a little bit more intuitive. There are other sorting algorithms as well. So, let's see. Okay, you all have seen bubble sort, so I guess I'll go kind of quickly through this. But I'll go ahead and just run through an example first. So, can you erase this? Keep forgetting I should just leave the array up there. Okay, let's see. Okay, so start off with this array, same thing we've been using, but now we'll talk about bubble sort. Selection sort is basically you go through the whole array one time and you just find the maximum. Bubble sort is a little bit more fine-grained, if you think of it. And the way it works is basically, instead of looking through the whole array to find the maximum, you just look at a pair of elements, an adjacent pair. So the first iteration of bubble sort, you look at these two elements. And what you do is, if the right element is less than the left element you're looking at, then you just perform a swap. And you kind of keep moving up every iteration like this, so you don't skip elements. You go one at a time, and you keep performing these local swaps. And what ends up happening is basically, if you have this 11, for instance, let's just go through a couple of iterations. So in this case, in the first iteration, nothing changes because it's the correct order already. But now we see this 11 and 9 here, where the 9 is less than the 11. So you perform a local swap. And now you go to the next pair. You perform another local swap. So this ends up being 11. That's 3. Look at the next pair. That becomes a swap because 11 is still greater. And now we've reached a point at which 11 is less than the element we're looking at. So we can just move on. We don't need to do any swaps there. So now we have 15 and 7 that we're comparing. We need to swap these. And then finally, we look at 15 and 6. We need to swap these. And so in the end of this, go ahead and erase that. At the end of this iteration, our array looks like 1, 9, 3, 4, 11, 7, 6, 15. And so now we once again see this kind of cool property where, because of the nature of these swaps, we ended up with the greatest element right here. And so we don't even need to look at that. That's actually where the name bubble sort comes from. So every time you look at these comparisons, you can potentially perform a swap. In the case of 11, we actually swapped several times. So you can kind of think of it like bubbles in like a bathtub, where this value just kind of pops its way all the way to the top. And if you ever go to an element which is greater, then that one just keeps moving along. And you end up with the largest element in one iteration moving up to the maximum position in the array. Alright? Does that make sense? Okay, so let's go ahead and just continue a couple more iterations. Like selection sort, after one inner loop iteration, the array is not quite sorted. You just have this element right here which is sorted. So let's do these comparisons. This is correct. This needs swapping. This needs swapping. And tell me if I'm going through too fast through these examples. Okay. So we see 9 and 11. That's correct. We see 11 and 7. And then we look at the last iteration and perform a swap. So once again, the behavior we see is here. You see 1, 3, 4, 9, 7, 6, 11, 15. And now, since we've bubbled up the second iteration, or the second, cycle of the inner loop, then we now have two elements which are correct. And you can see this procedure continuing. So let's finish it off quickly. So 1 and 3 is in the correct order, 3 and 4 is in the correct order, 4 and 9 is in the correct order, 9 and 7 is in the incorrect order. So we'll swap those, and then 9 and 6 is also incorrect. We'll swap those. And we move this bar here. And we have this array. So we perform the same sort of thing. Compare these two elements, compare these two elements, compare these two elements, compare these two. And finally we have one that's wrong. 7. And now we end up with a sorted array. But bubble sort's kind of dumb, so we'll just keep going anyway. We'll compare these two, then these two, and there's no swaps. We'll move this down. These two, no swaps, move it down. And then you're left with these two, no swaps involved, so we'll move it down. And once again, we finish on this last element right here. So after, almost n iterations, n-1 iterations of the inner loop, which is doing that bubbling, then you have a sorted array. Okay, does that algorithm make sense? Any questions? Yeah.
With bubble sort be long, slower than selection sort, since it takes longer to swap than fail?
Yeah, that's actually a very good point. So you may have noticed a similar pattern where you have n elements initially, then n minus 1, then n minus 2. So it's the same number of total iterations as selection sort, which is n times n plus 1 over 2. The difference here is that in selection sort, you perform one swap per iteration of the inner loop. With bubble sort, you perform one swap every iteration of the inside the inner loop. And so you're potentially also swapping n times n plus 1 over 2 elements. Whereas with selection sort, you're going to swap a maximum of n elements. So yes, in a long-winded way, yes, it is slower. Even though it has the same number of iterations, each iteration takes a little bit longer. Okay, any other questions? That was good. Okay, so let's talk about the code for this. Go ahead and erase this. And we'll just leave that interface the exact same, but rename the function to bubble sort. Okay, so we have that similar sort of thing where the outer loop is just going to be moving that bar from right to left. So x is going to start off at side minus 1, and x will go down to 0, and then x will subtract at every iteration. The inner loop for bubble sort is a little bit simpler. So we're still performing a whole for loop inside. And it starts off at 0, it goes up to x, and iterates by 1. Okay, so you may have noticed I did a less than x this time, where selection sort was less than or equal to x. So does anyone know why that would be the case?
You're looking at the element to the right, and the one to the right of x would be one that's already sorted.
Well, so in most cases it'll be one that's already sorted, but in the first iteration, the element you're looking at would actually be here, which that element doesn't exist. And so you actually perform one less iteration. So y from 0 up to that bar, except this time we don't include that element, the last element. And we just have to check the two local ones. So if a of y is greater than a of y plus 1, then we can use that handy swap function we created and send in our two indices. So this is a little bit easier than the selection sort just because there's less to keep track of, but you're performing a lot more swaps. And so bubble sort almost always will end up being a little bit slower than selection sort. So a couple of things just on the efficiency of bubble sort. For one thing, we realize that this many iterations, it's actually a little bit less because we're not doing less than or equal to here, but it's on the same order as this thing right here, which is the same order as selection. But one thing you may have noticed, at some point when we were going through this example, it looked like this. The array looked like this, and we didn't perform a single swap in the entire iteration. So if you keep track of, let's say, bool swapped, and you say that's equal to false, and you only set it to true if you perform at least one swap, then you can slightly improve the performance of bubble sort by if not swapped. So if you didn't perform a single swap in that entire iteration, then that means your array is already sorted and you can just return. And so that's a small optimization you can potentially come up with for bubble sort. In fact, this has its own name, and I mentioned bubble sort is dumb, so naturally this one is called smart bubble sort. And it just has this early termination condition where if the array is already sorted, then you don't need to spend more time performing these inner loops. And since this kind of got out of hand, so this is one loop, and then that's your outer loop right here, and that's your function. Okay, one last little thing about bubble sort. So it definitely has more swaps than a selection sort, but can any of you think of what the worst case for a bubble sort might be? Like in terms of some arrangement of elements that would just really show how bad bubble sort is. Yeah, so if the array is reversed, then every single time you call bubble sort, you'll perform a swap. So this condition will always be false in every iteration, and so you'll have just basically a whole bunch of swaps which you could have prevented with selection sort. Okay, so is bubble sort clear now? Okay, yeah, this I guess if you guys are familiar with this, then did you write this in C before, or was it assembly? Assembly. Okay, so you can see that that's a lot nicer. Okay, can I erase this stuff? Okay, so now I'm going to talk about something that was brought up a little bit earlier, and someone said one way of sorting might be to partition your arrays and then sort each individual path. So I'm going to go and just, oh, this should be enough space. So let's draw that same thing again. Okay. So one thing I want to mention before I get into this algorithm, it's called merge sort. If you have heard of that, then kind of get to learn it. But let's say you have two arrays, just 1, 3, 4, and 15. And then you have 6, 7, 9, 11. Let's make this a little bit more interesting. These two. Yeah. Well, 4, 6, and then move this 9 here. 7 here. So let's say we have these two small arrays. Okay? And we want to turn this into one big array. You'll note that each of these small arrays is already sorted. So if you have two sorted arrays, can any of you think of a way to merge those two into a single larger array in kind of an efficient way? Okay, no problem. So this is actually this problem that you'll see in the next lab, where you have to perform a bunch of set operations, which sets are really just arrays, but you have to perform them efficiently. And like I said, we'll talk about kind of efficiency in the next lecture. So you have to write these algorithms, but they have to perform in a certain amount of time. And so this is one of them. If you have two sorted arrays, how do you merge them? You can think of this as a set union. So one way, most efficient way I think, is you keep track of two elements, one from each array. And all you do is you take the lesser of the two elements, then you increase that index by 1. So in this case, you have 1, which is your lesser of the two. So you increment that, and you just copy 1 into this larger 8-element array. Now you see 3 and 4, so you copy a 3 in and move this. Now you see a 7 and a 4, so the 4 is less this time, so you move that side. Then you see a 6 and a 7, you copy the 6 in, move that. You see 7, move it. You see 9 and 15, pick 9, then 11, and then you just increment that off into like nowhere. And then you see that 15 is the last element remaining, and you just copy that in. So how many iterations does this take? If you have n elements, then how many times do you, I guess, increment the pointer? N times, yeah. N, so it's n over 2 in this side and n over 2 in this side for a grand total of n iterations. So keep this in mind. I'm not going to write the code out for merge sort simply because it would take up like 3 of these boards. So I'm just going to go like a high-level algorithm. So given that you have this merge function, I guess, at your disposal, let's say you have this array, this unsorted array. You can partition this in half and just basically do nothing. Like just literally partition it in half. And then you have 2 subarrays and partition those in half. 4, 11, 7, and 6. And then partition those once again in half. And so you end up with 8 single element arrays. I mentioned earlier a nice property of a single element array is that a single element array will always be sorted. And so let's take that to our advantage. We have all these single element arrays. So we've broken it down. Let's take each of these subarrays and just merge them into groups of 2. So we'll start off with 1 and 11. And if we perform a merge on that, then it's pretty straightforward. It's already in order. Then we take this next group of 2, which is 9 and 3, and then merge those 2. And once again, the merge operation is O of n, or not O of n, it just takes n iterations. So in this case, 2 iterations. Then we look at the next batch, which is 4 and 11. Merge those two, and then we have the last one, which is 6 and 7. Alright, now we have these pairs, each of which are 2 element arrays which are already sorted. And so let's go up one more level, and let's merge these 2 pairs of 2. So if we perform the merge algorithm on these, we'll first copy a 1, and then a 3, and then a 9, and then an 11. And if we perform it on this group, copy a 4, then a 6, then a 7, then an 11. And now we're almost back where we started. We have 2 subarrays. So we'll go up one more step, and we'll merge these 2. So we see these 2 arrays that we're merging. We see 1 is less than 4, 3 is less than 4, then 4 is less than 9, then 6 is less than 9, then 7 is less than 9, and then 9, I think I copied one number.
Your original one
Yeah.
has 2 11s.
This should have been 15, sorry. Yeah, that was the original array, right?
Yeah.
Okay, let's go and change this. So yeah. You could do it with the 11s, but just for consistency, so you know to have like one array that you're doing all this on. So 7, then you see 9, and you have 11 and 15, and you merge those. And now, all of a sudden, you're left with one array, which is sorted. So now comes the big question. How long did this take? How many iterations did this take? And it's not immediately obvious. So this division is just simple pointer arithmetic. You just subdivide it into 2 pointers. So we'll consider that like no time at all. This merge step, in this case, took 2 iterations, 2 iterations, 2 iterations, 2 iterations, for a grand total of n iterations. This one took 4 and 4, and I'm talking about merging single things into bins of 2. In this case, merging bins of 2 into bins of 4 takes 4 iterations for a grand total of n, or in this case 8. And then you perform one more of these. This time you have 8 total, which once again is n. And so you've performed n iterations, and how many times did you do that? Log 2 of n. And the reason it's log 2 is similar to like binary search was log 2, because we took our array and kept dividing it in half, which takes log base 2 of n time. And then in each of those, we perform n iterations. So the grand total here is n log base 2 of n. And so once again, comparing just like binary search versus linear search, we had n versus log n. In this case, we have this thing, which more or less, if you ignore some of these other things, is equal to n squared. So n squared versus n log n, you can see, like, let's say you have 128 elements. I don't know what 128 squared is, but 128 times 7 is, like, 768. No, it's not. But basically, it's a lot less iterations than 128 squared. Okay? So I'm not going to go into the details of that sort. I'm not sure if you ever see it in this class, in terms of like actually coding it. But now you know that it exists, and you can see it a lot better. So something interesting about merge sort, there's 2 sorts of classes of sorting functions. One of them is more or less n squared, which includes selection sort, bubble sort, and one called insertion sort. Then there's another class which is n log n, and that sorts like quick sort and merge sort. So as it turns out, and you'll actually do like a formal proof in your algorithms class if you take algorithms. It turns out it's actually impossible to sort a random array in less than n log n time. So it may have a couple of like factors where like maybe it takes like 20 less iterations. But in general, like it will never leave the parent function of n log n, and you'll actually see like a formal proof in your algorithms class, which is really cool. So that algorithm approach is like basically being optimal for sorting a random set of elements. Okay, any questions on merge sort? yeah, once again, you may not need to know that, but it's just kind of cool to see that, it doesn't look like you're storing anything, you're just splitting the array and like merging it. But in nlog n time, somehow you magically have a sorted array. So yeah, those ones are less intuitive, but they're still like, those are obviously more commonly used than these ones. Okay, one last thing. We still have a few minutes left. So we'll go ahead and erase this. I just want to tie all this back into the user database that we talked about in the last lecture. So, we had a user, and the user had some stuff in there, but most notably an email address, which was a char pointer, or just a string. And then we had this user database, which had an array of users. And then we had a size. And then we mentioned we have this function which returns a user pointer, and it was called search, and it took in a database, and an email address. All right, so using those, using that setup, let's quickly just write a linear search and a bubble sort that you could perform on this customer database. So at the beginning of the lecture, I mentioned it's a lot easier to do these examples with elements that are integers. So what do any of you guys know, like fundamentally, what makes an integer easier to work with in a string in terms of sorting and stuff? Yeah, easy compare. So we've talked about this strcomp function, string compare, which it looks something like this, where you have an int that's returned, and then two strings, so s1 and s2, and it returns a 0 if the two strings are equal. And by equals, I don't mean like the two pointers are equal. I mean like the strings themselves, the characters in the strings are equivalent. So what we haven't talked about is, well, we mentioned it returns a non-zero number if they're not equal, which makes sense. But actually, it returns a negative number if S1 is less than S2, and a positive number if the other condition is true, where S1 is greater than S2. And so now, all of a sudden, using the string compare function, we have basically easy access to a comparison for strings. So let's use this function to create just a search, a quick search. So this is going into that function. We go through X, which goes up through each element in the database, which is in D arrow size. And inside here, if we string compare D of users, X, and then extract the email address from this, and we compare that to our email address, and that's equal to 0, then these two strings are equivalent, and we can return the user. And it'll actually be a reference to this guy, because we're returning pointer. And then if this isn't correct, we talked about this earlier. When you have pointers, the way of signaling a failure is by returning null. Where null is just defined as just 0. This is the equivalent of returning the number 0. So this would be a search in the context of the user database, and you'll notice this looks very incredibly similar to the linear search we did on an integer array. The key difference here is we have this string compare, which is performing the comparison for us. And we have a little bit of like indirection where we have to access like the user's array indirectly through a different pointers. But the whole template looks basically exactly the same as linear search. And so if you take that same interface right here, and you impose the assumption that the user database will be sorted by emails, then using this exact same template, this exact same like header, then you can just replace the inside of the function with a binary search. And now you've improved your performance from n time to log n time, log base 2 n time. And you never have to change the interface. And so that's kind of one of the beauties of object-oriented programming, which we'll get into that more. But basically defining functions, having a clear interface with everything you need is really nice because you can change out the guts without like breaking anything else. So I have a couple more minutes. I'll just quickly go over like a sort. So if we do a bubble sort, it'll look pretty similar. So it'll be d goes size x. And then in here we'll do a for loop that goes from 0, just less than x. And then the key change here is we'll perform a string compare. So remember, if you recall, we perform a swap when the left element is greater than the right element. And so I'll abbreviate a bit, but let's say users y users email users y plus 1 email. If this is less than this, it'll be negative. If this is greater than this, it'll be positive. And so if it's greater than 0, then we perform that swap on the database. So d and then y plus 1. And then we can close that off. And once again, this looks really similar to the bubble sort, but the difference is you have a string compare instead of just a less than sign, and you have a couple of layers of indirection. Okay, so any questions on that? All right, the n stuff that we talked about, like n squared, all that, that's what we're going to be covering in the next lecture. The professor is going to be back, so he'll do that. But yeah, it'll be kind of a natural progression from this stuff. Okay.